Hello, so this video is intended to illustrate some additional examples of element reductions. We're going to start with reducing a complicated resistor network into an equivalent resistance. So you would do this kind of scenario whenever you might be connecting a complex circuit to a voltage source or current source, and you want to understand the equivalent behavior of the entire circuit with respect to a couple particular points. So a couple nodes here. So I've pulled those nodes out of the circuit right away to illustrate that. This is example 2.29 in the textbook, and in this case all the resistors have equal value of R. Specifically, R is 10 ohms in this case. So what we're going to do is attempt to find if something was connected to these 2 points here, what would be the equivalent resistance of this entire network seen from that perspective. Okay, so there's a couple ways to go about doing this. I'm going to show you what I think is the best way to do it. There are others, and you're welcome to explore that. The first thing I like to do is go ahead and identify all of the nodes in the circuit, and we're going to just label them. We'll call the nodes that we're going to start from A and end at is going to be called B, so we're not done until we find all paths possible from A to B. Okay, so the additional nodes, let's see, one thing we quickly identify is that A, again, wires are not unique nodes. We see that A is actually connected to all of these resistors connected to this blue highlighted area here. We have to propagate these because that's a single node. They're perfect conductors. We have a unique node over here we'll call C. We have a node right here called D. There's only two things connected to D. And we see that B is actually connected across this entire bottom segment. So we have a lot of resistors connected to that one. Okay, so we actually only have, even though this looks fairly complicated, we have 1, 2, 3, 4, 5, 6, 7 resistors. We only have 4 nodes. So what we're going to do is redraw this circuit to look a little bit more convenient. So we're going to start at A. You can start at B and go to A, or A to go to B. Okay. Starting at A, but I'm going to draw this going from left to right, just like we're used to reading. That will make it a little bit easier. So what I'm going to do is I'm going to look at the original problem. Since I've identified A as being everything connected to this node, I count those elements. So I've got 1, 2, 3, 4 resistors coming out of that node A. So I'm going to draw a split and 4 paths coming out of A. Okay, so let's go down the pipeline. So in this first path on the top, that's just a single resistor. On the other end of that, that goes to node C. So let's label that. Okay, I'll cross that out so I don't count it again. Next, I've got this resistor coming out of A going to C. Also to C. Let's cross that one out. I have this resistor here coming out of A going to B. Cross that one out. And I have another resistor coming out of A going to B. Alright, so now you might see right away I've got 2 C's, so let me just go ahead and join those up into a single node to make it a little bit easier. B, I'll join those up to a single node. Now note that this path is actually completed. It goes A to the end B, but this one's not, so we got to continue it on, and eventually it's got to go to B. We're not done until all of our paths go to B. And I forgot to cross that one out. Okay, so that means we're continuing on at node C. What's coming out of C that hasn't already been counted? So there are 2 additional branches coming out of node C, so I'm going to draw a split into 2. Okay, the first one right here, cross that out, goes from C to D, just like that. The second one goes from C to B. Cross that one out. Okay, we actually have another path for current to flow that goes to B. Okay, so that one's done. We still have one more that's not completed. That's just the one connected to D here, and it's a single resistor that goes to node B. So we can see right away that that's a series connection that goes to B. Okay, so now we've got all of them going to B. Let's just join these things back together. I can do this, connect those together that way, and maybe I'll just draw those down to connect them that way to my final node B. Okay, so this circuit on the bottom is exactly the same circuit as on top. I just redrew it to maybe look a little bit easier so that I can combine these elements a little bit simpler. Okay, so let's do so. See if we identify anything in series and in parallel right away. So I note that at node D, I found that these two resistors are in series. You might have identified that from that picture right away. So we'll take those two resistors, find the equivalent resistance of that path from C to B going through that particular resistor is going to be a summation, so that's just R plus R, which is 20 ohms. At this point, you could redraw it if you want, or find any other ones that you can combine right away. One other one that I see right away is that these two resistors that we started with are both share nodes A and C, therefore by definition they are in parallel. Call that R2. So that's R in parallel with R, which is R over 2, which is 5 ohms. Likewise, we see right below that two resistors sharing nodes A and B, so those are in parallel. Call that R3, which is also R in parallel with R, which is going to be 5 ohms. Okay, so at this point, it would probably serve us to redraw this. So you have A. Now going into two equivalent resistors, R2 and R3, so each of these being 5 ohms. Top one is node C, bottom one is node B. Out of C, we get a split into two, where that top one is the 20 ohm resistor, the bottom one is the 10 ohm resistor, which is node B, at which point it gets connected up with the bottom path to our final node. Okay, from here we can see a couple other combos that are convenient. The 20 ohm and the 10 ohm are in parallel, so let's call that R4, just 20 parallel 10. That is 6.67 ohms. And you might see that this equivalent resistance, 6R4, is in series with the 5 ohm. Call that R5 is equal to what we had called R2 plus R4, which is going to be 11.67 ohms. Redrawing one more time if needed. Now we have this equivalent resistance between A and B on the top path as 11.67 ohms. The bottom one is 5 ohms going to B. We see that these are in parallel. So the final R equivalent between A and B is 11.67 and parallel 5, which is 3.5 ohms. And that's our solution. So we could redraw that complex circuit between A and B as a single resistor of value 3.5 ohms. So one way to think about this is for the top circuit connected to any voltage or current source, it will behave in an identical manner to this single resistor of 3.5 ohms shown on the bottom. Now, if you were tasked to find a specific parameter inside this circuit, for example, the voltage across this resistor highlighted in the middle, you would not want to reduce this into a single resistor of 3.5 ohms because you would lose the information about what's happening internal to that. This is just a model for the behavior between A and B. So if what's interesting is purely the behavior describing the relationship between nodes A and B, then reduce the system.